Hello my scholars, you are welcome to my school YouTube channel and my name is Frank. In this video, we are going to be learning electromagnetic field. Now we started this topic in our previous video. So in today's video, we are going to be looking at the part 2 of it. So relax, do not go anywhere, I'll be right back. You are welcome back to my school YouTube channel. In today's video, we are going to be looking at electromagnetic field part 2. So before we begin with our lesson, let's quickly run through the objective for today's video's lesson. So objective number 1, state and explain Faraday's law of electromagnetic induction. 2, state and explain Lenz's law and the implications of the law. 3, explain the principles underlying the production of direct and alternating current. 4, explain the difference between the construction of an AC and DC generators. 5, explain the principles of a transformer and induction coil. 6, state the uses of induction coils and transformers. 7, explain why the coils of the induction coil and transformer are laminated. 8, explain why it is preferred to have a high potential difference instead of high current transmission over a long distance. Then number 9, solve simple problems on power losses. So let's move to the next slide to begin with our lesson. So on this first slide, we are going to be defining what electromagnetic induction is. So electromagnetic induction is simply the production of current or voltage in a conductor when there is a relative motion between the conductor and a magnetic field or magnet. Okay, so that is just the simple definition of electromagnetic induction. Okay, so when a bar magnet is moved horizontally towards the end of a solenoid coil connected to a center zero galvanometer, it is observed that the galvanometer deflects. Okay, so when we say center zero galvanometer, we are referring to a galvanometer that its needle, okay, points at the center of the scale where no current flows through it. Okay, so that's what is meant by center zero galvanometer. Okay, showing that a current has been induced in the coil. On moving the magnet away from the coil, it is observed that the galvanometer deflects in the opposite direction. Similar deflections are observed when the magnet is held stationary, while the coil moves towards it or away from it. No deflection is observed when both magnet and coil are stationary, with the magnet either inside or outside the coil. This shows that no current is induced. When the speed of the movements is increased, the deflection is found to increase. So let's move to the next slide to see the diagram of what we are trying to explain here. Okay, so this is a solenoid and this is a magnet showing the different movements of the magnet. So this is when the magnet is moving towards the solenoid coil, and this is when the magnet is moving away from the solenoid coil. So let's see some facts about electromagnetic induction. And one of them is that current, that is the induced current, will flow in a galvanometer whenever there is a relative motion between the coil and the magnet. Like we said in the previous slide, when there is no movement between the coil and the magnet, then the galvanometer will not deflect. Okay, so number 2, the induced EMF or current depends on 1, the speed of motion of the magnet or the coil. Of course, the magnet can move or the coil can move. So one of them can be stationary while the other one moves. Okay, the faster the speed, the larger the induced EMF or coil. So these are some of the factors that determine the induced EMF or current. Okay, so one of them is that the speed of motion of the magnet or the coil. So the faster the speed, the larger the induced EMF or current. 2, the number of turns of the coil. 3, the strength of the magnet. And 4, the presence of a soft iron core inside the coil. So let's move to the next slide. Then the last but not the least facts about electromagnetic field is the direction of the induced current reverses when the direction of motion of the magnet or the coil is reversed. Of course, we actually saw that in the explanation after the definition of electromagnetic induction. So let's talk about flux linkage. Okay, so when a magnet is brought near a solenoid, the magnetic line of force, which is referred to as flux, and this flux spreads out from the magnet, links the coils of the solenoid. So this phenomenon is known as flux linkage. Okay, so the magnetic lines of force move whenever the magnet moves or the coils move relative to the magnet. This movement causes a change in the magnet. Flux, magnetic line of flux linked with the coil. Thus, an induced EMF or current is produced whenever there is a change in the magnetic flux linked with a coil. With an open coil, this change produces an induced EMF, but not an induced current. So mathematically, the total flux linkage phi, okay, is given as BAN cos theta. Okay, where B here, okay, of course, on the next slide, we will see what each of these letters represent. So let's move to the next slide. So now let's talk about direction of induced EMF in a straight conductor. And we are going to do that using Fleming's right-hand rule. Okay, so the Fleming right-hand rule states that if the thumb, the forefinger, and middle finger of the right hand are mutually at right angles to each other, with the forefinger pointing in the direction of the feed and the thumb pointing in the direction of the motion, then the middle finger will point in the direction of the induced EMF or current. So this is just the pictorial explanation of Fleming's right hand rule. Okay, so this is the thumb pointing or indicating the direction of the feed, and this is the forefinger, okay, pointing, this is the thumb pointing in the direction of the motion, okay, and the forefinger, this is the forefinger pointing in the direction of the feed, and why this is the middle, okay, why this is the middle finger, okay, pointing in the direction of the induced EMF or induced current. Okay, so record that the force on a current carrying conductor of length L in a magnetic field B is given by F is equals to BIL. Okay, of course we have sine theta, okay, but when theta is equals to 90 degrees, then we'll be having F being equals to BIL. So that's exactly what you are seeing on the screen. So let's move to the next slide. So, but remember that power is equals to force times velocity. Now remember that power is equals to work done all over time, right? But this can as well be written as F times X over T. So this S over T is equals to V. So that's why we have power to be equals to force times velocity. But also remember that electrical power is IV, right? And remember, mathematically, in one of our videos, I think that should be when we are talking about current electricity, we were able to prove mathematically that this V is also equals to E. So in place of V, we can replace it with E. So they are power. So in this case, we can equate them to one another so that that power is also equals to EI. Okay, so if we equate this to, but remember that F from the previous slide, okay, we saw that F is equals to BIL, right? So in place of this F, we replace it with BIL. Hence, we have BILV being equal to EI. So I will cancel out I, so that at the end of the day, we have E, which is the induced EMF, to be equals to BLV. Okay, so let's explain what each of these letters represent. So the capital letter E represents induced EMF, the B represents magnetic field strength, or you can as well call it flux density. L represents the length of conductor, and this length of conductor is perpendicular to the magnetic field. Okay, while V is equals to velocity of conductor and is also perpendicular to the field. While E is maximum, okay, that is the induced EMF is maximum when L and V are both perpendicular to the field. okay, why E is equals to 0 when L or V or both of them is parallel to the magnetic field. Okay, now let's move on to state the laws of electromagnetic induction. So basically we have two laws of electromagnetic induction, and these are Faraday's law and Lenz's law. So let's move to the next slide to see these laws. So let's begin with the first one, which is Faraday's law of electromagnetic induction. So Faraday's law of electromagnetic induction states that whenever there is a change in the magnetic flux linking a coil or circuit, an EMF is induced, okay? And this EMF is proportional to the rate of change of magnetic flux linking the coil or circuit. So from Faraday's law of electromagnetic induction, we have that the induced EMF is directly proportional to change in phi and inversely proportional to change in time, okay? So E, of course, this is just a relationship, so we'll have to introduce a constant, right? So E is equals to minus K, then the phi all over dt, and we'll call this equation 1. So K is a constant. Then this minus is actually from Lenz's law. Of course, when we get there, we'll talk about it, okay? So K is a constant. Now equation 1 is consistent with the expression F is equals to BIL if only K is equals to I. Therefore, E is equals to minus the phi all over dt. But remember that phi here is the magnetic flux, is the total flux linkage, okay? I will call this equation 2. So equation 2 can also be written as E is equals to minus N the phi dt, where E is equals to induced EMF and N is equals to number of turns in a coil. So let's move to the next slide. Right, so the phi all over dt is equals to rate of change of magnetic flux in 1 turn, and the unit of the phi dt is Webers per second, written WBX minus 1. Okay, and the magnetic flux linking a coil depends on 1, the magnetic field strength, 2, the number of turns in the coil, and 3, the area of each turn. So these points are worth taking note of. So let's move on to state Lenz's law, okay? And that minus is as a result of Lenz's law, okay? So Lenz's law of electromagnetic induction states that the direction of induced EMF is such that it tends to oppose the motion or change producing it. Okay, so that is the answer. That is where that minus in the formula on the previous slide came in. Okay, so this diagram is just illustrating Lenz's law. Okay, so let's move to the next slide to explain what this diagram represents. Okay, so moving the north pole of the magnet towards the coil causes the face A of the coil to acquire a north polarity because an anticlockwise current is induced on the coil when viewed from face A. This north polarity opposes the motion of the magnet by repulsion of like poles. Moving the north pole of the magnet away from the coil causes the face A of the coil to acquire a south polarity because a clockwise current is induced on the coil when viewed from face A. So you can actually see that on the diagram in the previous slide. This south polarity opposes the movement of the magnet by attraction of unlike poles. Now remember that we said like poles repel and unlike poles attract. So basically that's what we are seeing here. So Lenz's law is an application of the law of conservation of energy. And why is it an application of the law of conservation of energy? Because when energy is expanded, okay, is expended, the induced current flows, and the source of this current and the source of this energy is the work done when the magnet moves with respect to the coil. It must experience an opposing force. Okay, so this is also worth taking note of. Okay, so you might be asked, why is Lenz's law, or explain why you think or you feel Lenz's law is an application of the law of conservation of energy. So you tell them that Lenz's law is an application of the law of conservation of energy because when energy is expended, the induced current flows, and the source of this energy is the work done when the magnet moves with respect to the coil, okay, and it must experience an opposing force. So here's an example for us to lay our hands on, okay. So a wire of length 30 centimeter is moved with a speed of 2 meters per second at right angles to a magnetic field of flux density 0.4 Tesla. Calculate the EMF induced in the wire. So let's move over to the board to provide answer to this question. Okay, so remember that the induced EMF E is given as BLV. Of course, we actually showed how this formula came about. Okay, so in this question, we are given length to be equals to 30 centimeter, which we have to convert to meters, and that will be equals to 0.3 meters. Then we are given the magnetic, or we are given the flux density to be equals to 0.4 Tesla, and then we're also given velocity to be equals to 2 meters per second, right? So these values will just substitute into these formulas. So that will be E will be now equals to 0, okay, 0.3 times 2 times 0.4, okay, times, then the L is 0.3, then times V, which is 2. So this will be equals to 0.24 volts, right? Since we are talking about EMF, okay? So this is the value of the induced EMF. So let's return back to the screen to continue with our lesson. So let's move to the next slide. So now let's talk about the applications of electromagnetic induction. So we have many applications of electromagnetic induction. So let's begin with the first one, which is the alternating current generator, or also known as alternator, or you can as well just call it AC generator. So this is the diagram of the AC generator. We have two permanent magnets, we have an armature, we have the slip ring, okay, and we also have the carbon brush. Okay, I think it's the slip ring that actually differentiates this from the DC generator. So let's talk about the essential features or the structure of the AC generator. So the AC generator consists of an armature, and the armature is a rectangular coil consisting of a large number of turns of insulated wire wound on a laminated soft iron core. Then we have a magnetic field created by the curved poles of a horseshoe magnet or an electromagnet. Let's move to the next slide, please. Then we have two copper slip rings, arrow 1 and arrow 2, to which the ends of the rectangular coil are connected and which rotates with the armature. Then we also have two stationary carbon brushes which are made to press tightly against the slip rings and to which the circuit is connected. So those are the essential features. Now let's talk about the working principle. Okay, by means of a mechanical drive, the armature is made to rotate at a steady speed about a fixed axis in the magnetic field provided by the horseshoe magnet or / electromagnet. As the armature rotates, the coil cuts through the magnetic flux, thereby causing a change in the magnetic flux linking the coil. This change in the flux linking the coil produces EMF in the terminals of the coil by electromagnetic induction. Hence, an induced current flows in the circuit with external load, which is connected across the terminals of the coil by means of the slip rings and carbon brushes. Let's move to the next slide. The direction of the current reverses every time the plane of the coil passes the vertical position. This reversal of current direction is rapid. That is, it happens many times in 1 second. This type of current, whose direction reverses rapidly, is called alternating current. So alternating current is one whose direction reverses rapidly. A revolution is called a circle, and the number of circles which the current goes through in 1 second is called its frequency. Okay, and in Nigeria, the suitable frequency for a domestic appliances is 50 Hz. Now let's talk about variation of EMF and current with angular displacement over time in an AC generator. So one, if at the instant the rotation begins, that is when theta is equals to 0 degrees and time is 0, the plane of the coil is vertical with arm AB up and CD down. AB and DC are moving parallel to the magnetic lines of force, and no cutting of flux is taking place, meaning the rate of change of flux linking the coil is 0 and no EMF is induced at this instant. Then number 2, between theta is equals to 0 degree and theta equals to 90 degree, the induced EMF increased from 0 to maximum. Let's move to the next slide. Now, if the plane of the coil is then parallel to the field, that is when theta is equals to 90 degrees and T is equals to T1, with the arm AB on the side of the south pole of the magnet, AB and CD are moving at right angles to the field at this instant. There is maximum cutting of flux taking place, meaning the rate of change of flux linking the coil is maximum and the induced EMF is maximum at this instance. That is when theta is equals to 90 degrees. Okay, take note of that. The induced EMF is maximum. Okay, the induced EMF is maximum and the rate of change of flux linking the coil is also maximum. On further rotation of the coil, the induced EMF reduces until it becomes 0 at theta equals to 180 degrees and T is equals to T2. Now remember that T there represents time. When the plane of the coil is vertical with arm AB down, here again the rate of change of flux linking the coil is 0. Between theta is equals to 180 degrees and theta is equals to 270 degrees, the induced EMF increases from 0 to maximum, but its direction reverses at theta is equals to 180 degrees. At theta is equals to 270 degrees and T is equals to T3, the plane of the coil is now parallel to the field again with the arm AB on the side of the north pole of the magnet. With AB and CD moving at right angles to the field at this instance, there is maximum cutting of flux and hence maximum rate of flux linkage leading to maximum induced EMF at this instance. So let's move to the next slide. Between theta is equals to 270 degrees and theta is equals to 260 degrees and T is equals to T4, the induced EMF reduces from maximum to 0 at 360 degrees, where its direction reverses again and the circle continues. So the graphical representation of the variation of the output of an AC generator is a typical sine curve or sine wave as shown below. So basically this is what we are trying to explain, okay, on the previous slide. So now E is equals to minus the phi all over the T, but phi is equals to BAN cos theta. Okay, so in here we just impute, in place of phi we replace it with BAN cos theta, so that E is now equals to minus D all over the T, then BAN cos theta. Of course, we can rewrite this to be equals to E is equals to minus BAN, then D dt cos theta. So if we differentiate cos theta, okay, with respect to time, then we'll now be having E to be equals to BAN sine theta d theta all over dt. But remember that d theta all over dt is equals to omega. Okay, so that E now becomes BAN omega sine theta. So just take note of that. And remember that when we differentiate cos, it's going to give us minus sine. So minus times minus, that will be equals to plus. So that is why there's no more minus here. So just take note of that. So let's move to the next slide. Now, when theta is equals to 90 degrees, then E is equals to BAN omega, and that is equals to EO, right? E subscript O, meaning maximum induced EMF, okay? So that E is equals to maximum induced EMF sine theta, okay? But remember that theta is equals to omega t, okay? Remember that theta is equals to omega t, angular velocity, okay? Therefore, E is equals to maximum induced EMF then sine omega t. So where E naught is equals to maximum value of induced EMF, okay? Now let's talk about alternating current, AC. So like we said earlier on, alternating current is a current which changes continuously in direction while passing through a conductor. It's a current which changes continuously in direction while passing through a conductor. So an alternating current can be measured using one, the hot wire ammeter. An alternating current can be measured using one, the hot wire ammeter. And this hot wire ammeter works on the principle of the heating effect on current, or it depends on the heating effect of current. So let's move to the next slide. Then two, this alternating current can be measured using the moving iron ammeter. And this moving iron ammeter works on the principle of magnetic effect of current. Then three, an alternating current can as well be measured using a moving coil galvanometer. Okay, but here you have to be careful. To do that, you have to connect the galvanometer, or you have to attach a rectifier to the galvanometer so that the galvanometer can convert the current from AC to DC. Okay, now let's discuss about the hot wire ammeter. Okay, one of the instruments that can be used to measure AC current. Okay, so let's talk about the structure. One, it consists of a resistance wire connected to the terminals of the ammeter. Two, we have a silk thread connected to the midpoint of the resistance wire, and the thread passes through a pulley. Then three, we have a pointer attached to the pulley. The pointer deflects over a non-linear scale when the pulley turns. Okay, so when we say a non-linear scale, we are saying the scale is not a straight line scale. Okay, it's not like a ruler. So it could be something like circular. Okay, it can be circular in shape, right? Now, the scale is calibrated by passing currents of known values through the wire. The non-uniformity of the scale is because the heat produced in the wire is related to the current by H is equals to I square ROT, making the scale a square law scale. Okay, so the scale used here is a square law scale. Let's move to the next slide. So what is the working principle? Now let's talk about it. When current flows through the wire, it heats up and expands, thereby making the wire to become slack. The slackness of the wire makes the silk thread to become loose, no longer taut. By the action of the spring, the thread is pulled round the pulley, which is now free to turn, and the pointer attached to the pulley moves over the scale. The heating effect of the current does not depend on the direction of the current, and this is also very important to take note of. The heating effect of the current does not depend on the direction of the current. Therefore, the hot wire ammeter is suitable for measuring alternating current and also direct current. So meaning that we can use the hot wire ammeter to measure both AC and DC, that is to measure alternating current and also measure direct current. So this is just the diagram of the hot wire ammeters, and this is the square law scale. Okay, this is the wire, this is the pointer, and this is the spring, this is the pulley, this is the terminals. Okay, so this is where we bring the preview of today's video to a close. Okay, you can watch the complete video by simply clicking on the link in the description below, and that will take you to my school website. There you will have to subscribe to enjoy the complete video. So in the complete video, you will learn about the transformer, you will learn about the induction coil, you will also learn about self and mutual inductance and many more. So I believe you enjoyed the preview of this video you just watched. If yes, please do not forget to hit the like button, click on the subscribe button, and lastly, tap on the notification bell to get informed as soon as we upload the next videos.